Welcome back, everyone. We will continue with chapter 3. As we have seen in chapter 2, what we have actually focused on the rocket performance, and one of those most important parameter in a rocket equation, if you look at it, is that effective exit velocity (CE). So I've mentioned before that to deduce the CE is not easy because it's an in-flight performance. But when we want to manufacture a rocket engine, we will indirectly basically calculate, or rather, we have to estimate the actual exit velocity at that engine level. Then we need to tolerate during the flight to get the actual CE. So basically, this whole chapter 3 is going to talk about or look into how are we going to successfully estimate our exit velocity, because as you know, exit velocity is one of the most important parameter in the rocket equation. In fact, if you look at the rocket equation, it is indeed the effective exit velocity. So in order for us to calculate the effective exit velocity, we should be optimizing the exact exit velocity of the engine, which governs the rocket performance, which will actually help us to thrust the rocket forward. We will have a look at types, or rather the techniques, that actually how we can estimate this exit velocity. So therefore, this whole chapter 3 is going to focus on parameters like surface ratio, for example. We will talk about it later. The temperature ratio, the density ratio, and basically pressure ratios. So all these ratios are very important parameters, in fact, in order for us to successfully come back and calculate or estimate the exact exit velocity. So that is very important to understand. So the whole chapter 3, I can preamble to all of you saying that the focus will be basically how we are going to coin the WE, which is the exit velocity. Indirectly, we should be able to calculate maybe the temperature of the engine, temperature ratio of the engine, the pressure of the pressure ratio of the engine, the density of the engine, then of course maybe the surface ratio, that we will have a look at it as well. All right, now if you look at a rocket business, if you look at chemical reaction in fuel, which is basically directly heated rockets. So if you can imagine, if you have a rocket engine, in order you have fuel already, definitely. So you need to actually burn the fuel, so to say. So there are methods basically where you directly heat the fuel, or direct heated rocket, you call it. It's just like car. Car would be practically a direct heated engine, because the burning takes place directly in the chamber. So you can imagine that we will start basically categorizing the chemical reaction, or rather the rocket engine, by looking into the chemical reaction in the fuel itself. The first type is basically, if you look at it, directly heated. So now, as far as the fuel is concerned, so if you look at it, the fuels, basically the chemical fuels, or you may have also the nuclear or fusion fuels. We will see that there are also nuclear engines that actually there is an option basically to look into nuclear engines, but it is not popular when it comes to Earth-oriented mission. This will be the energy source. You have energy usage, then of course what you're going to produce is the thrust. So all this fuels is going to go into the combustion chamber, so to say, where actually you get that fuel with the oxidator. Typically will be going to be a mix, and then you ignite, and then you have basically the exact combustion. So when you have the combustion, then what you do the expansion, and you know, typically just like in aircraft engines, you have nozzles basically to catapult basically, or give you a thrust of the actual burning. All right, now this is a simple or typical, very typical, I would say, fuel. Then you have the separated from the energy source. The fuel is separated from the energy source, which means that you have external heatings can take place. So external heatings can come from basically the sun, or maybe nuclear, or even laser, for example. So you can imagine there is basically this fuel, there is an external heat is basically is given to the fuel, and then you get the combustion. Sometimes this can be also coined as electrothermal engines. Basically, if you have a separated, the fuel is separated with that actually energy source. And we will look into a few of the options later part of the lecture: arc jet, or even a radio frequency gas. These are basically a very typical, I would say, electrical engine, and that is a chapter for all of you, basically to go through later part of this semester. And you have direct thermal engines, which is, well, this says that basically the heat is actually from planet Earth. Basically, before you start actually launching, you may have electrical power supply. Is injected, or rather it is being pumped into that actual combustion system. Or even you in the spacecraft itself, that means you have an engine, but then the energy source comes from the spacecraft to basically to ignite the fuels. So these are typical ones that actually you have, where you have the fuel is basically kept together, or sometimes actually the fuel is being separated with the actually energy source. So there are two types of directly heated rocket engines. Indirectly heated would be, again, if you look at it, indirectly heated as two categories are put here, basically nuclear energy or nuclear fuel. This is very, very, I would say, uncommon for Earth-oriented mission, but it exists, has been researched on. There are models already, in fact, to look into these options basically for space application. Then you have also the solar array or even solar wind. Remember, solar basically in satellite technology, we have also seen that actually we are for Earth, or rather any Earth-bound missions, satellite missions, basically we have a photovoltaic panels basically to generate that electricity. So therefore, there is a source of energy which can be used in order basically to ignite the fuel. What it means. So you have these are the options that we have, and here if you look at it, we have heat exchangers, because the heat basically, when you talk about reactors, when you talk about nuclear material, definitely there will be a heat exchanger, because there will be a huge amount of heat basically for you to dissipate and to cool down the system. So there are a lot of technology basically is available. MHD is Magneto Hydrodynamics. We will see some of the options actually in this later part. Then you have that famous electrical engines basically for the rocket application also. So all this basically, again, the type of burning, whether it's direct or indirect, you end up basically in introducing or pushing them to the exact expansion, to the nozzles, so to say, in order for you to get the push or the thrust. Okay, go on. All right. Before we start looking into all those equations, because we need to actually develop, or rather we need to deduce the equations, let us actually get the basic, I would say, diagram or even the basic definitions correct. Now, P, I would say that you can see is a pump or even the fuel tank. Okay. Then you have the combustion chamber that you have, and the nozzles you have. What we need basically, if you have a fuel, heat has to be injected inside, because that will actually ignite the fuel, and then you have combustion and outgas is out. Therefore, thrust factor is going to be parallel to the flight direction. So that is the basic principle that you have to understand. And we are going to actually, all those equations are going to be based on this. Okay, a bit more, go on. A bit more detail on types basically. What I have given you here, closed loop combustion chambers, basically that means you can imagine that there is a combustion chamber, there is a fuel, there is an oxidator, they pumped into the combustion chamber and is ignited. Just like you can imagine, for simplicity reasons, you can imagine just like in the car engines. So that's typical ones. Right. Examples basically. Chemical rockets, chemical reaction, that means that you have a fuel and an oxidator. Now, we are more and more, if you look at it, in chapter 1, all those performance, rocket performance that you have calculated or estimated are basically of chemical rocket. This is very, very common. In fact, most of the launches that you have, commercially available launches, are basically chemical rockets. That's here. Then you have surge rockets, basically you have water heaters, okay, coal gas engines, you have expansion of coal gas basically. It is, for example, hydrogen can be the fuel, and then you just pump out the hydrogen, in fact, that will give you also thrust. These are basically coal gas engines. Then you have a nuclear heater. Now, please do understand that what I've listed here, all those options available for space application, but not necessarily all these have been used for Earth-oriented mission. More importantly, the chemical rocket engines are very typical, and most of our calculations are going to be focused on chemical rocket engines. Okay. Then you have electrothermal, as we have discussed just now. You have resistor-heated jets. Okay, we will cover that in later parts. And there is something quite interesting for interplanetary missions as well. Sun radiation rockets. For example, you have parabolic mirrors to focus basically the heat into the exact spot to ignite the fuel. Hybrid, you have a chemical and electrical energy sources. There are hybrid engine. Then anti-material, nuclear-based is for future basically application. So what you have seen is so many concepts are available basically if you want to travel to other planets. In fact, there's so many options available, but not all is basically technologically is ready to be picked up. So that is very important. And just focus on chemical rocket engines. Now, temperature distribution. You need to understand this. Now, most of you have seen a lot of, I would say, not a lot, but I mean examples of rockets. And I've also shared to you there are basically, if you look at the bottom of the rocket, there are nozzles, okay? And nozzles dissipate, I would say the nozzles dissipates a lot of heat actually. So this heat is going to be dissipated to the, where exactly? To the environment. So why not, most of the concepts in a rocket technology basically to heat up, to use that actually the heat basically to heat up the fuel so that the fuel will be very, very optimum in terms of the pressure, in terms of the exact, I would say pressure, plus the amount of heat basically. So you are adding an additional heat which is going to be dissipated, you're harvesting it and heating up the fuel before you burn the fuel. That's what it means. So therefore, if you look at, and it also helps to cool down. If you look at it, the fuel will run through the skin. If you can see, there is actually piping basically which goes over with the nozzles in order to harvest the heat. So when the heat is harvested, that heated fuel will be injected into the chamber, burning takes place. So therefore, you are actually optimizing the heat and plus the burning as well. So if you look at the actual temperature, it also helps to cool down the nozzles in a way. So if you look at it, temperature, when there's no fuel, the temperature is so high, but with the help of the fuel, you are not only cooling, but you are also preparing the fuel to be injected into the chamber, the combustion chamber. So it's a very, I would say, win-win situation, so to say. You are not losing the heat, but you are reusing the heat basically to prepare the fuel before you burn the fuel. So if you look at it, typically, if it's a liquid hydrogen, so what you do, you have a turbine, but this is a nuclear sort of solution, which is, I just want to actually share. There are actually nuclear concepts, nuclear engines, which actually runs this way. So as we know, basically, when we start actually dwelling with nuclear, there is huge amount of basically heat that can be used. So what you do, basically the pumped fuel goes into, and then goes through this nozzle, and again, you will be basically heated up, and then you pump out basically or purge out the actual gas. So therefore, you get a thruster. Okay, so this is basically not only managing the heat, but also basically optimizing the exact fuel burn. So that is important. But remember, nuclear basically options are not common for our Earth orbit mission. So, but the exact reheating of the fuel, it is also being done even in chemical rockets. Go on. All right. Just not mentioned sun radiation rocket. As you can see, if you have some parabolic reflector, you have the sun basically shining to this parabolic reflector. So what exactly you focus basically, you focus the parabolic reflector to a particular spot, heat element, and the heat element will be get heated up. Therefore, the fuel will be also heated up. So it's ready for burning, and the same, it goes to the expansion. This is the nozzle. So there are these concepts, but as you can see, it's not common at all basically for Earth oriented mission. Okay, but this concept is there. All right, go on. Now, I have introduced a diagram basically how our rocket engine should be modeled, and based on that, what we are going to do now is that to coin all those important parameters before we start actually dwelling with the equations. Now, the definition: rho, density, as all of you know; P, pressure; H, enthalpy; V, volume; A, cross section. A is cross section. A is cross section. Surface is this surface. So you have two two important surfaces are actually important here. Basically, you see, when you look at the nozzle, the around it, inside, if you look at it, that's on the surface of the nozzle inside. It's very, very important to really look into the profile of that exit velocity. Okay, then you have the cross section. More often than not, you can see this is a good circular cross section. So when you cut through the nozzle, you will have a circular cross section. So that is one cross section basically. And then when you move towards to in, then the cross sections get smaller, as you can imagine. Okay, and the surface is around it from the throat, it gets bigger. So that you must understand, the surface and the cross section. So the surface inside, the cross section is basically, as you are looking at it, that is your cross section. So this is very important parameter. Q is a velocity vector. W of component W basically is what is our main aim here. W is a component of the Q actually. The velocity vector W is one of those components. So this is what is critical for us to measure in an experiment or in terrestrial application, because when you measure the WE, then we will know what could be our CE. Because when we say that ideal case, all of us want WE, exit velocity, is equivalent to the effective exit velocity. But in the real application, what happens? The WE would be definitely will be bigger than the effective exit velocity. Or what I'm saying, the exit velocity will be lesser compared to the theoretical, or rather the actual measured WE, because WE is being measured in the terrestrial environment, in fact in the lab, etc., in the manufacturing plant, etc. So that is the important item that you need to remember. P, pressure. Where this pressure is, this is in a combustion chamber, this is the throat, this is the cross section of the throat, this is the cross section of the nozzle at exit. PA is pressure, atmospheric pressure. So these are the terms actually you need to really understand. Huh? So note that the CE is effective, it's exit velocity, but we didn't write here effective exit velocity here, but I just want to make sure that you remember that exit velocity is directly calculated, but we need to calculate the WE in order for us to get the exit velocity. Okay, and then indexes, stationary condition. If I stationary condition, T throat, E exit, A is ambient, as you can see. Now, more importantly, please do revise thermodynamics. I'm very sure you've been exposed to thermodynamics. It is very important. That's one thing. Second thing, you have also seen, you have gone through, I think, a propulsion. That also becomes very useful to follow through this actually chapter. I'm not going to deep dive into lots of actually theories, because that theories should be basically been exposed to you in thermodynamics, likewise in the propulsion. So that please take note of that. Huh? Okay, let's move on. All right, this is the first equation that is important. At the end of the day, what we want is the thrust, F. And it's nothing but double integration of rho W, exit velocity, with respect to that exact surface, and a delta P, the difference of the pressure. Difference of the pressure of, basically, if you look at the chamber pressure and the atmospheric pressure. The more pressure that you have, the better exit velocity that you will have. Okay, now note here, you must understand why we are doing the double integration, because there is a two surface area that is important here. One is basically the surface, which I've said, the surface inside the nozzle. Then another one is basically the cross section itself. So the skin surface and the cross section. So there is basically two areas is involved in order for us to get a three-dimensional. Where this can be actually also, this is actually is a absolute value, but we can actually calculate this in 3 dimensions also, x, y, and z. There's no problem, okay, because that profile can be also extended that way. All right, now let's look at an average nozzle cross section. That means for average nozzle cross section basically. Obviously your rho will be also an average, and your exit velocity is also going to be average, and this is going to be at the exit of that nozzle. Okay, so the F, and which is equals to basically the delta. This is also exit. That means the exit pressure of average also as well. Okay, and the atmospheric pressure. So at the exit of the gas, there will be a very high amount of pressure actually. Then you have an atmospheric pressure. So this is important basically in order for us to actually give you the thrust. Now, what this is equivalent to, technically speaking, this is supposed to be equivalent to that mass flow and the effective exit velocity. Okay. Now, look at this. This is what is happening, and this is supposed to be equivalent to a corrected effective exit velocity actually. Okay. Now, atmospheric pressure also changes when the flight progresses. So therefore, you can imagine this is not constant throughout the flight. Atmospheric pressure is not constant throughout the flight. Although you can produce a constant exit pressure at PE, that means at the nozzle you can produce a constant exit pressures. Let's say, but the delta will vary depending on the atmospheric pressure. Now, if you look at the trajectory from point A to point B, atmospheric pressure, you can't control it. It changes. Therefore, this keeps on changing. Which means that the exit velocity will become an effective exit velocity. Will be actually lower, in fact. Okay, will be much lower. Alright. Now I can redefine the CE. This formulation CE is the thrust over mass flow. This you have been exposed to, which can be also written in terms of WE. That means exit velocity. Okay. Now thrust coefficient. That when you can have the exact F, which is the thrust, then all we need to know, you have to give me what is the P naught. P naught is your pressure at the chamber, and the throat. That would be actually giving you the thrust coefficient, and it can be very well expressed with WE or simply with the CE as well. Alright, but in order for you to look at the thrust coefficient or rather calculate that, you must know the actual chamber pressure and the throat, right? Cross section of the throat is important. Alright, this is an ideal case. If PE, the exit pressure, is equivalent to the atmospheric pressure, the thrust will be smaller, okay, when PE, that means exit, is lesser than the atmospheric pressure. Basically what I'm saying, if you have this condition, don't fly the rocket engine. No point. Can you imagine the exit pressure is lower than the atmospheric pressure? You can never have a good outgas basically to thrust the rocket. Okay? So this is fine. You say that the exit is almost same. Okay? But if you becomes lesser than that, then that means that something is not well designed in your engine. Alright. If you do a double integration, basically we can practically find that exact thrust basically. Yeah? We can exactly find that this one. This is going to be a delta P, in fact, delta P with respect to the exact surface. Alright, go on. Alright, I have also in chapter 2, we have also discussed about how basically to look at the exact efficiency. Now, if you look at here, enthalpy is an important measure because your engine design is important. But the fuel that you use is also important, okay? Which means that the enthalpy of the fuel is also very important in order for you to produce a good WE or eventually CE. So therefore, selections of the fuel is also pretty crucial here. So let us see the enthalpy of HO, basically, the combustion heat, okay? Delta R, combustion heat, constant pressure, and HR is basically the fuel average enthalpy. Okay, So this N delta H is basically the heat loss. Normally, if you have in a heat loss due to kinetic heat loss, you can say this is a kinetic heat loss. So when this happens, practically, you will have a different enthalpy if kinetic losses are being calculated. But otherwise, what we can say, we can assume that there's no heat or friction losses. So therefore, this term, there is no losses. Almost H naught is going to be constant. So we say we neglect that the kinetic loss. Okay, that will be constant. I guess this has been also been explained in thermodynamics, if I'm not mistaken. In an ideal case, expansion in chemical and thermodynamics is balanced. So PE, pressure at exit, TE and HE are zero. So therefore, what you have, nozzle is loss free. So then this you should be able to, this I think in chapter 1 I have also used this formulation practically. When you want to calculate the W max, it's nothing but basically the function of the enthalpy itself. So this is important will help you in order for you to look at, if I use this fuel, what you think my maximum W max I can get. That's what it says. It gives you a good start in order for you to choose the fuel that is desired for a good W max. Alright. Alright. Now for the thrust, basically, if you look at it, for F max or F ideal is in vacuum. So therefore, this formulation actually can be used. It is nothing but basically your m dot with respect to your enthalpy as well. So for typical liquid hydrogen and liquid oxygen, so let us actually calculate the exact enthalpy. And when we have an exact enthalpy, technically speaking, your W max can be actually calculated. Now, what is important to understand here, you have already calculated the W max. That means the W exit velocity maximum, but the CE always would be actually lesser than this. So you can't expect more than this, in fact. That's what it says. So alright, I should be able to have with this fuel, I have W max. Let's say here in this case, 5,000 meter per second. Alright, is it enough? Is this enough for me to carry my payload from point A to point B? That you have to decide. Okay, then you choose the fuel. Alright, it's good, it's enough, fine. Then you are happy with this fuel. Alright, go on. Now ratios, Vmax and Fmax, the thrust ratios. The thrust ratio basically is equivalent to is nothing but equivalent to CE over Vmax. Okay, so this is a very important formulation. So if you look at it, it means that my correlation between the exact velocity, exit velocity, and the actual thrust that I produce is a very closely basically related. So in order for me to extend this formulation, I can have a thrust vector, in fact. Okay, such what is that? Efficiency. In terms of the efficiency, your thrust coefficient, that we can actually see. Now, your typical I would say effective engine, the best engine that you can have, this would be 1. Okay, the ratio should be 1, but you will never have this 1. Okay, you will never have this 1. So all these ratios, how beautiful if you can have an engine where all these ratios are practically is 1. But it's not going to happen. Yeah, it will never happen. Okay, so always basically this is going to be good. Okay, and we presume that we do it for the vacuum because half, let's say when it's during the start, it is not vacuum, it's ambient pressure. That means atmospheric pressure. But then when you start actually going further up, you're almost in the vacuum environment. So we say that, okay, fine. Let's say thrust coefficient, CF in vacuum. The relevant inner efficiency, this I think we have also calculated in chapter 1. I've invoked from here and then reincorporated that. Incorporating losses in efficiency are basically radial velocity losses. Now, all these are important. You see, when you have a nozzle, obviously you would like the exit velocity to be parallel to the exact flight direction. But sometimes there are basically radial velocities. So that will be creating losses. Then the profile are not perfectly a square profile. The best square profile, basically, why you say the square profile, because when you have a velocity profile coming out, you want a square profile. Reason being, the magnitude of those exit velocities from top to bottom is constant. That's the best, but probably not. More often than not, on the side you will have a lesser magnitude, and then the middle you have a slightly higher magnitude. So the profile will be something like a parabolic profile. You can see later, we will see that also in our lecture. Then you have a heat to environment, that is losses, friction, kinetic friction losses basically are there. Okay, kinetic losses in terms of the friction is also there. Then your PEP exit bigger than, of course, 0. Then you have unbalanced exit flow as well. So all these are actually, there's so many losses, and now we can understand why we can't have this one. Why are we having CE lesser than WE max? Is because of so many losses are there when we start actually flying the engine. Okay, practical inner efficiency would be obviously F, whatever thrust that you have, and the F ideal that you foresee or you calculate. So, but for P atmospheric bigger than 0, the estimation is obviously PE would be more or less, we say that with the atmospheric pressure, equal to atmospheric pressure. This is a typical way actually we start doing the estimation. Go on. All right. Ideal rocket and ideal gas fuel. So what we say that, let us assume that the gas fuel that is rushing up from the nozzle is an ideal gas. So as we have learned in thermodynamics, we can use all those equations in thermodynamics in order for us to estimate here. The first one is basically variable, velocity is the same, temperature T, density, and the pressure. Now ideal gas, PV that I think all of you know, equation 1, that is ideal gas equation. Energy balance, this practically CP control pressure, or CV is control volume. I think you know in thermodynamics. Energy balance, we can say that this is actually a delta enthalpy, and it is related to your exit velocity. And also we can actually write this. This is also invoked from your thermodynamics equation. So impulse balance would be nothing but W and exit velocity and a function and a plus basically 1 over the exact density. It is equals to 0. So you have already 1, 2, 3 equations are there for us, and the equation of continuity, the typical equation that m dot rho v actually, or WA is constant. All right, and this is a very typical equation that actually you have. Now using equation 2 and 3, I can actually deduce for W, basically the velocity W is eliminated, so therefore I have the delta H over dP is the pressure, this is enthalpy, and the rho, so equals to 0. Therefore the change of entropy, the S, okay, this is equivalent to this formulation. So now for DS0, practically there's no change. That means you have a constant state such that there's an isotropic flow is achieved. So this is quite typical in fact, if you have learned turbine gas, this is a very common one, common formulation actually we use. So we have picked from thermodynamics basically to apply in this particular subject or this particular chapter in order for us to deduce the actual equations. On further. Alright, an isentropic condition. So when you have an isentropic condition, you have this equation can be invoked. So for control volume, control pressure, CP, CV, okay, your heat capacities, CP over CV I coin as kappa, and CP minus CV is R basically, and therefore CP can be actually written as R, and of course with the function of kappa. For adiabatic isentropic condition, basically we can have a relation between kappa, which is CPCV, the temperature and the pressure itself. Right? This is a very important ratio. You have the pressure ratio, so I can rewrite the pressure ratio. Can rewrite the pressure ratio in terms of the temperature ratio as well. Obviously, with square of kappa basically. Yeah. Now, applying equation 1, okay, and I can actually have this formulation as well, which is the relation between the exact density and the temperature, okay. Therefore, for those parameters, basically the exact condition are basically we held that constant. So therefore, the velocity W for equation 2 to 5, it can be actually rewritten in terms of kappa. Alright. Now, speed of sound, if I introduce here, why? Because I should be able to express all these equations in terms of Mach number as well. I coin speed of sound A as actually it's a square root of kappa RT, and the Mach number basically I can actually rewrite the Mach number in terms of the W. Alright, so looking at this formulation, I'm looking at an option of obtaining probably the temperature ratio. I have also pressure ratio, maybe density ratio, maybe. Let's see what we can actually get out of all this actually formulation. Go on. There you go. Now, this is an important slide. Ideal rocket and ideal gas. Temperature ratio. T naught is your chamber and T is your exit. So I have a ratio. So I can find the temperature ratio in terms of the kappa, CPCV, and the Mach number. Mach number is going to, the Mach number of what? The Mach number of the exact gas. Okay, the gas, the outgas. So very importantly, I have now temperature ratio, I have the pressure ratio, I have the density ratio in the function of kappa and Mach number. So which means that, hey, life is now easier now. I just have to measure what fuel that I'm going to use. Let's say I have a fuel, so I can actually I can calculate the CPCV, or rather it comes with the CPCV already. Okay, then I should be able to technically estimate. If I can estimate the pressure, if I can measure the pressure, I should be able to estimate what is that Mach number for this particular flow. So indirectly, what I have here, it seems that I should be able to calculate what is my W. That's a good news. So applying the pressure temperature ratios in equation 6, the velocity now yields into this formulation. This is the exact formulation that we want in a rocket engine for us to estimate W here. Terrestrial. That means in planet Earth here, before we fly, we manufacture the engine, we want to measure, estimate the WE. This is how we can actually do it. Now, if you look at this parameter, can we know the kappa? Kappa is CPCV. Yes, you know what fuel you are using, you should be able to tell me. This is basically is a gas constant of the particular gas that you are involved. Whatever gas actually you, let's say for air, yeah, but this is not going to be air, but this is the gas constant. T, temperature, pressure ratio. So when I can measure, how can I measure temperature in an engine? I have a temperature sensor. How can I measure the pressure? Pressure sensor. So I have these sensors in the engine setup. I should be able to estimate my WE for this engine. It's done. That's how this is always been done for rocket engine. So the W, that means the exit velocity, cannot be directly measured, but normally it is indirectly measured by using this equation. You should be able to do so. The pressure and the temperature ratios can be experimentally determined. Therefore, I should be able to calculate. Because to measure the exact W, it is so difficult because which spot that you want to measure. If you look at a nozzle is very huge. Whether you want to actually take it very near to the skin of the nozzle, center of the nozzle, you want to average that, this is very difficult. Okay, so what the best way basically you want to do, or best solution is that to measure the actual pressure, to measure the actual temperature, and you know what fuel you are going to use, technically speaking, you are done. So it's much easier to measure the temperature than the velocity itself. Alright? Go on. Alright, optimum nozzle cross section. Okay, invoking equation 3 and 4 like this now. This formulation can be rewritten. M dot over A is rho W. Okay, the flow at a nozzle means at the throat. Okay, the flow at the throat from this equation. What we say is that, now if you look at this, is quite interesting. What I coin is that the W, the velocity, is basically at throat. There is a velocity at throat as well, but obviously it is at the convergence of the throat. There is a velocity, so I coin this as a Wt. Now the gas velocity at the throat, let's say it's about, let's say, Mach 1. Now At, I can still calculate the velocity of the throat. W at the throat can be also calculated by kappa and the temperature. Okay, and obviously, what is the velocity? The velocity also depends on the exact temperature of the chamber inside. The gas is used. What gas is that? And this will be giving you the exact A naught. So I should be able to also know what is the exact velocity at the throat, which is not so critical compared to the exit velocity at the nozzle or exit of the nozzle. Okay, go on. This is just for an exercise. Go on. Alright. Equations 2 and 7 are employed here. So I know that density, that means the differentiation of the density basically over density is equals to basically the ratios of W. That means W over A2. A2 is at the throat. So I substitute the continuation equation for this formulation is obtained, and this is final formulation. Now at the cross section, that means the ratio of cross sections, I want to know what is the exit and the throat. Exit and the throat. Okay. Now exit and the throat cross section ratio, very simple. If you look at it, give me the Mach number. What is the flow rate? The velocity rate basically. Kappa is given. I should be able to actually have this done. So what it says that if you want to optimize, you want to calculate the exact diameter of the nozzle, this equation is very important. This equation is extremely important because the diameter, the throat, let's say we fix the diameter of the throat, then we want to optimize the exact exit diameter of the nozzle. This equation is extremely important for you to use. The optimum Mach number can be obtained from pressure ratio equation. There you go. So particularly called expansion ratio. This is the expansion ratio is to this formulation. So this is also is important. So now in this chapter, you need to remember temperature ratio. You need to know how to calculate the temperature ratio, pressure ratio, density ratio, and surface ratio. Okay, this is an expansion ratio, so to say. Okay, it's a surface ratio because you want to design the exit of a nozzle. This equation is the most important equation. Okay, go on. All right. So let us actually study, or rather look into some options. You have let's say 3 cases here. Let me start with the easiest one. This. Let's say the gas flow m equals to 1. Well, Mach number is equals to 1. Mach number equals to 1 would be sonic. Okay. Mach number more than 1 supersonic, more than 5 would be hypersonic. Then you have more than 1 is supersonic. Then you have also less than 1. Less than 1 would be subsonic. So there are 3 cases basically. 3 cases. So now let's say for the gas, this is the easiest one. Let's say this exact nozzle. This is a cross section of the nozzle. So let's say that the throat and the exit is the same, just like a pipe, a duct. So there is no, basically the dA over A, that means that the variation of A over A is of 0. So variation over A and A0 basically is a duct. You look at it, what it tells you that I can never have a high pressure, I can never have a high exit velocity. So is this good? Can your nozzle design be like this? No, never. So which means that your throat and your exit is the same. No, you can't fly a rocket with this. So let us have another option. Bigger means supersonic. The throat is big, the exit is small. P is larger, but W is smaller. Why P is larger? Because the pressure comes here into a very smaller channel, the pressure will increase, but unfortunately the velocity is smaller. What about we do otherwise? Throat and exit. Looks like we have some important thing here. P is smaller, obviously. P is here bigger. Here, P would be smaller, but it seems that W is bigger here. This could be a good option. What about this one? Subsonic. Bigger throat, smaller. Obviously, P smaller, and here is V is larger. But remember, these are basically a subsonic. That means a very, very low, very low, very low. So in this case, this may not be actually a good option, although it's larger, but it is not good enough. Okay? This is actually probably the best. Here, because of the flow is quite slow, what do you have here? P is larger, obviously, and the throat is larger, and smaller here, the P will be smaller, but W will be actually again smaller. So it looks like among all these, this is the best option that we have. That is the reason normally what you see, the nozzle of any rocket engine will be in this shape. That means throat will be smaller, and then towards to the exit will be larger. And the reason being is that your P, your W, you can get bigger. Okay, go on. Alright, so let us actually study a bit on how that we have talked about pressure, we have talked about temperature, we have talked about the Mach number, okay, and we have also, we have said actually throat, okay. So let us see. Now, what exactly happened here? If you look at the, and of course the velocity, velocity. Now, if you look at the pressure and temperature, the pressure and temperature, this is I cut across the exact engine, and throat is in the middle, and this side is going to be your exit, and this side is going to be your combustion chamber. Alright, and your throat is in the middle, if you can imagine. Alright, there's the engine just now. So at this side, that means at the combustion chamber, pressure and the temperature definitely is going to be high, right? High. Then when I'm going to travel to the throat, then I'm going to travel out. Obviously, my pressure is going to be dropped, because just now we have seen the pressure is going to drop. Likewise, the temperature is going to also drop. Whereas, if you look at it, my velocity and my Mach number at chamber, it is going to be minimum. You can say before the ignition it will be almost zero. After ignition, it is going to come out. The gas is going to flow out, and goes through the throat, and then conversion happens. At the throat, conversion happens, you have a spike of the velocity and the Mach number together. Okay, so two major parameters drops from maximum to minimum. Two major parameters that what we wanted, which is the exit velocity. The Mach number is important, and of course the exit velocity. When exit velocity high, obviously Mach number will be high. From minimum or zero before ignition, goes through the throat and spikes out. This is exactly what we want. Okay, go on. All right, ideal rocket and mass flow and thrust. All right, mass flow. This is a very typical formulation in thermodynamics. Rho basically AT. So what I can actually have, I can rewrite this in terms of the function of basically kappa. Okay, kappa. And if I can measure the pressure, if I can measure the temperature, I should be able to measure the actual mass flow, m dot. This is important for the fuel. So I can rearrange this. I can say that m dot is this formulation, and I just say that, well, my gamma is a function of my kappa. So I can write a very I would say compact formulation of m dot. This is important for you. Now, if you look at this formulation again, T naught, which is the temperature in the chamber, you can measure that. Pressure you can measure. This is a gas constant, and AT, you can measure that. You can measure. So you should be able to calculate the m dot as well. Alright, exit gas. This is a typical formulation that we have been introduced before as well. Note, the pressure ratio is this. This is re-invoke again. Therefore, WE, I rewrite this again. This is same like what you have seen before. It's just that I've clustered them. You put all this together, you will actually read the same WE that what we have defined just now. So what you need to measure here, it says also the same thing. You need to measure the temperature in the chamber. You need to give me the actual pressure in the chamber. The exit pressure, I should be able to tell you as well. Maybe it's an atmospheric pressure, then I can just assume it's an atmospheric pressure. And the fuel that you're using, that will give me CPCV, the ratio of CPCV, kappa. The whole thing actually should be giving my WE, this enthalpy based on the fuel. Okay, so again the same formulation, I repeated this. You have seen a new formulation, but I repeated this. This is the same like what we have defined before, WE. Okay, the square root, basically everything is inside is the same. All right, go on. Okay, this will be the thrust, m dot WE, AE, then exit pressure over the atmospheric pressure. Now employing 7 and 8, so basically the thrust yields again a beautiful formulation with the kappa and the pressure ratio, the surface ratio. Okay, then you should be able to actually calculate the exact thrust. So there are many ways, depending on what are the temperature, what are the basic parameters that you have, we should be able to calculate the thrust. And the thrust coefficient, basically thrust coefficient runs between 1 to 1.8 to 2.1, sometimes 2.2. It can be also calculated when kappa is known and those parameters. So what you are seeing here is that again and again I am using the pressure ratio, the temperature, then of course the surface ratio, basically for me to calculate the exact parameters. Okay. Now, particular conditions basically the always the atmospheric condition. So these are the vacuum conditions. Basically, you can rewrite that in terms of gamma and the kappa as well. So again, indirect measurement is needed. Pressure measurement is needed. Once the pressure measurement is needed, you should be able to calculate many rocket parameters because the formulation is ready. Now, importantly, don't forget, the idea is that we need to calculate the pressure ratio, the temperature ratio, density ratio, the surface ratio. When you have all this, you should be able to churn out all those important parameters for a rocket engine. The thrust, in fact, and the WE. Alright, go on. Okay, specific impulse. So you have learned specific impulse, maybe you have seen some specific impulse up to here. Okay, in the first chapter, how to calculate the specific impulse with respect to the pressure you have it here. So in the rocket manufacturer, this is how they calculate the specific impulse actually. Pressure ratio, and this is universal gas constant. So this is a mass of molecule mass. For example, if you say that it's just an air, that's it. It should be for 0.028 kilogram per mole for air. Okay. CPCP for air would be 1.4. Yeah, just an example. But then the exact gas actually that we need to know the exact basically mass that we should be given. All right. Rocket efficiency, kinetic energy base. Again, you have seen this formulation before, and I've used in terms of that exact pressure ratio. And thrust based on inner efficiency. Again, I rewrote this in terms of the surface and the pressure. Also, basically, the inner efficiency can be written as a pressure. So you see all those parameters that we have established before. We are now re-invoking back them, and we have measured the pressure, we have measured the pressure ratio, we have measured the temperature ratio, we have measured the density ratio, we have measured the surface ratio or expansion ratio. Using these ratios, we can plug into and then calculate all these parameters without any problems. So this is how the rocket engine designers or the rocket engine manufacturers provide you all those important parameters. Okay. All right. Again, surface ratio. Yeah, surface ratio is we have seen this in terms of gamma. Then you have nozzle. Nozzle. This is convergence. At the convergence, what will be your thrust? This is at the nozzle. Okay. Just now the thrust at F, when it's F alone, is an F at the exit, but at the throat or the nozzle, at the convergence, basically you have it as well. At the throat there is a force, so there's a thrust. So what is this? That is at the throat. So you can actually reformulate this, and then we can calculate the force at the throat. But this is you cannot be using this to for the rocket final thrust. No, this is actually at the throat. Effective exit velocity can be also calculated in terms of this. Now, why we can calculate here? This is basically at the convergence. At the convergence, we can calculate, but the exact effective exit velocity will be actually finally different than even here for sure. Okay. Then the thrust through the expansion, again the exact thrust over the exact convergence. That means throat arc exit. What is that ratio? The ratio is beautifully done with kappa, with the pressure ratio, with the surface ratio. So once you have these ratios, we should be able to calculate this. Now, why this is important? Basically, this is how you want to optimize. You want to optimize, for example, if you start changing this, let's say you try to the dimension of, let's say your throat. Basically, if you start changing it, you know that practically it's going to affect your force. So the ratio is important in order for us to design as well. Okay, go on.
This is
Okay, all right. I guess we will probably continue maybe in the next lecture to try to complete this chapter 3. Thank you.